So we're going to continue on with section 9.4b. Before I begin, I'm going to talk a little bit about our interval of convergence. This has been important for us because our series converges as long as whatever x value have is within the interval. Okay, but the problem with this is we have only IOCs for geometric series. In addition to the IOC, we're going to talk about the ROC, or the radius of convergence. And it is directly related to the IOC. Using this with our ROC, we're going to talk about a theorem that's going to be really important for us today, and it's called the theorem for convergence of power series. So if we have the sum of the series of c sub n times x minus a to the n has three possibilities. Is that your series is going to converge as long as the absolute value of x minus a is less than r. And it's going to diverge if the absolute value of x minus a is greater than r. We are not going to consider what's happening at the endpoint. The series may or may not converge when the absolute value of x minus a equals to. We could also have two other things. It could converge for every x. So if it converges everywhere for every x, no matter what you choose, then that means your radius is equal to infinity. Now it could also just converge only at a single point, x equals to a. And when we have that, we say r equals to 0. So let's do some examples. First one we're going to do is going to be very similar to what we did at the beginning of this chapter. I want us to find the ROC and the IOC for this series. So x plus 5 to the n power. I want the sum of that series. It's geometric. So if it's geometric, it converges when? The absolute value of r is less than 1, so I want that to be less than 1. Now take a look at this and how it matches up with what we have written up here above. It's in that same form. Absolute value of x minus a is less than r, so that tells you a is negative 5 and r is 1. Alright, so next thing, we've got a definition and a theorem. The first definition we have is absolute convergence. So if you have this series and you make them all positive terms, if it converges, then we say that that original series, a sub n, converges absolutely. So in other words, if you must take the absolute value of all the terms for it to converge, we say it converges absolutely. And there's a theorem that goes with this. If the absolute value of a series converges, then the series also converges. So what this means for us here is that absolute convergence implies convergence. The converse is not necessarily true. Let's do another example. I want us to find the radius of convergence for this series. So 3x minus 2 to the n over n. Let's take note of how this series differs from example 1. Okay, in example 1 it was geometric. Okay, this time it's not geometric because we've got this little n down here in our denominator. And because of this x up here, I know that this series doesn't only contain positive terms. So I need to find the radius. I'm going to use our ratio test, but I'm going to do the ratio test for absolute convergence. We're going to use the ratio test but throw absolute values around it. So it looks like this. This is basically what we're going to use. When we plug in our next term, that means we're going to put a sub n plus 1. So this is going to be 3x minus 2 to the n plus 1 over n plus 1. Then we're going to divide by a sub n. So I'm going to flip the fraction and go ahead and write that down here already. And I need to start canceling a few things out. So n plus 1 and n cancel because as n gets really, really large, n and n plus 1, those are basically the same. And over here, I'm going to cancel out 3x minus 2 to the n with almost all except for one of these 3x minus 2's. So I'm actually going to be left with a single 3x minus 2 in absolute values. So this is the same thing as just saying the absolute value of 3x minus 2, and the limit's gone. The series will converge if the absolute value of 3x minus 2 is less than 1. Now I'm going to try to write this in that same form as above in our theorem. So that means I'm going to divide everything by 3. Then I'm going to have x minus 2/3 in absolute value is less than 1/3. So that tells me that a is 2/3 and our big R is 1/3. So the radius of convergence is going to equal 1/3. Let's try another one. I want us to find the ROC again, but this time I'm going to make my series look a little bit different. I'm going to have n x to the n over n plus 2. So I'm going to use the ratio test for absolute convergence again, and that means we're finding the limit as n approaches infinity of a sub n plus 1 over a sub n. I'm going to write my limit. I'm going to plug in what I know. Be careful when you write this. This is now n plus 1 times x to the n plus 1 over n plus 3. Then we divide by the previous term. So I'm going to flip that fraction. So this is n times x to the n in absolute values. You are left with the limit as n approaches infinity of the absolute value of x. So again, there's no n's left to be affected by the limit, so all we have is the absolute value of x, and this is going to converge, or it converges when the absolute value of x is less than 1. This one should be easy. A is 0 and r is 1. Our radius of convergence is equal to 1. The very last thing that I want to go over today is a really special kind of series called a telescoping series. Here's our telescope, and we have this interesting, cool series that we're going to take a look at, and you'll see why in a few minutes, why we call it a telescoping series. Okay, so here's my series. I have 4 over 2x minus 1 times 2x plus 1. I want to find its sum. Now, I'm going to rewrite 4 over 2x minus 1 times 2x plus 1 as the sum of two separate partial fractions. So what I get to say here is that instead of having this series written as one single fraction, it's going to be the same thing as having a series that looks like this. 2 over 2x minus 1 minus 2 over 2x plus 1. So I want to write out some of the terms. So let's write out the first term. What is our first term going to be? N starts at 1, so when I plug in 1, I have 2 over 2 times 1 minus 1. So I get 1. Plug in 1 over here, 2 over 2 times 1 plus 1. So I get 2/3. So the next one we're going to do will be for n equals to 2. It's 2 on top. What's on the bottom? 2 times 2 minus 1. And then plug in on the other side, 2 over 2 times 2 plus 1. Now let's do n equals to 3. So that's 2 over 2 times 3 minus 1, and then 2 over 2 times 3 plus 1. You guys noticing anything? See these right here? What's going to happen with all of these terms? They're all going to cancel out, and since this is an infinite series, it's going to go on forever and ever. So what's the sum equal to? Everything beyond here is going to cancel out. There's only one thing left. This very first one. 2. The sum of this series is going to equal to 2.